Okay, good evening to all. So today we will continue with part number 4 for chapter number 4. Okay, so currently we are looking at radio transmission. So how we can have a transmission using the RF frequency. Okay, so yesterday we have seen the part 3 on the impedance matching circuits. Okay, impedance matching is actually you are calibrating the frequency that is modulated, and before you pass to the antenna for the transmission, so you need to have a certain parameters or matching in order to achieve the proper transmission, okay, between antenna and also the circuit. Okay, so impedance matching is happening in between the modulated signal circuits and also the antenna. So if you are not perfectly matching the antenna and also the circuit, so we have seen yesterday, so there will be a signal loss, so there will be components fuse, so a lot of complication can happen in the transmission. So we as an engineer, we need to come up with a solution for us to design the circuit for us to match together with the antenna. So in the production line, we can see usually the antenna will be developed by someone else, and the circuit will be developed by someone else. So when it comes to the place where we join, so we might have issue if we never properly match the antenna to the circuit. Okay, so yesterday we stopped with this slide. Is the final notes we have seen about the L network matching. So two limitation of the two element matching is restriction of the circuit Q. So Q is the quality factor of the circuit. Okay, so um, we know from this formula. So this is the formula to calculate the Q. So Q for the source and also the load. So we can see uh, the value of Q is heavily related to the value of RP and also RS. So the resistance. Okay, so practically we can put it in a different sentence. We can say RS and RL determine the value of Q. So if you have differences in this, so the value of Q also will differ. Okay, so it makes the designer of the antenna. So antenna have to be designed in a certain way. So let's say yesterday we have seen, so antenna is developed based on the resonant frequency. So if the resonant frequency is the optimum value of the transmission, so at the resonant frequency, the signal that you want to pass from one antenna, one transmitter to the receiver, will be optimum. So we want to achieve the complete transmission at the resonant frequency. But the problem now is, so the person who create the circuit for the modulation, so they have their own calculation. So and the designer of the antenna must follow them. So the designer does not have the freedom to specify circuit quality. So because, so maybe the designer, they have a different view. So they might say, okay, so if for this application, so if you transmit with this antenna with this resonant frequency, will be better. But if the circuit is not supporting, then they cannot use the antenna. So it become an issue for high quality or which using the narrow bandwidth, or even for the low quality application. Okay, so low quality meaning in terms of the quality of the transmission. Okay, so there are another element we call as a three element matching. So previously it was only two elements. Uh, so we have to address the issue of the quality flexibility, so that the antenna designer can have some flexibility in the designing of the antenna. So we can the designer can specify practical circuit quality required. So meaning before, so they already designed the antenna, so they already calculated the value of Q, and they tell to the circuit designers for the modulation. So they can request. So we want a particular signal to be produced at this particular Q. So then it can address the issue of the previous two element matching. So can achieve larger Q than what can be achieved using L network. So L network, it is only using two elements. So either inductance or capacitance, either one. So by having this flexibility, so you can achieve a larger Q. Larger Q means it can be high quality signal transmission. So we can achieve that using the three element matching. So there are two types of three element matching. So we call as a pi network and also T network. So both, it has a certain construct, certain differences, but both will use a three element matching. Okay, so we will see today. So what is pi network and also the T network. Okay, so pi we know is a symbol in a mathematics. It's a Greek word. So for so we even have a numerical value 3.142. Okay, so for pi, so but we are not using that pi here for calculation. So the pi here is actually the shape, so it will look like a pi. So we know the network from the pi symbol. So the pi symbol is like this. So it's like a incomplete box. So we can see, so the shape is here. So that's why this is called a pi network. So it can be referred as a 2L network. So we can see there are 2L network, 1 and also 2. So previously yesterday we saw only one L network, but here we have two. So 2. So there are two. When you are combining these two, so you can get like a pi symbol. Okay. So we see about the pi network. The 2L network are designed to mesh with a smaller virtual resistance between source and the load resistance. So we know we have a source resistance here and load resistance here. So in between you have a 2L network. Okay, so you have two. So in between here we have another virtual resistance. So virtual resistance, it is actually a small resistance in order to control. Uh, it's like for you to tune the antenna. So normally antenna, in the house also we can tune, right? So we can just change the direction, so in order to get a better transmission. So similarly in this circuit, so this virtual resistance, the function of the virtual resistance is to have a proper tuning. So when you have this virtual resistor, you can have a certain parameter that you can adjust. So you can adjust in order to get a better frequency transmission. Okay, so in pi network, the virtual resistance are much smaller compared to the another type of T network. Okay, so in this smaller virtual resistance, so we can see uh, if let's say the current is going through here, so it will not choose this path because so there is a higher uh, resistance or impedance here, so it will choose this virtual resistance which is much smaller. So we know when the resistance are smaller, so the current like to travel. So similar like our traffic, so we don't like to travel in a heavy traffic jam, right? So we prefer to travel when the cars are less. So similar, so the current will choose a less congested part, which is the R virtual. Okay, so this is a small resistance compared to combination of these two. Okay, so here it can achieve the load. Okay, so analyze, so we need to analyze each branch using the usual L network matching. So yesterday we have seen. So you need to analyze separately, and you need to analyze separately. So what we want to form, so at the end we want to combine all this. So XP1, XS1, XS2, R virtual, XP2, and RL in a one symbol. So that's how we do the analysis. Because if we want to do analysis like this, so it will be very tough. So you need to combine these two first, then you need to combine these three. So then you need to combine these two. So in order to get the resultant resistance that you can apply. So when you are using the pi network, because of this R virtual, so we can see the load resistance will be lower. So in this case, RS, the resistance of RS is actually the circuit, okay, and RL is the antenna. So you want to make sure so it can be matched. Okay, so that's the function of impedance matching circuit. Okay, so pi network. So design of each section of the pi network proceed the same way as the L network. So all the calculation will be the same. So the analysis, everything. So we are not really looking into analysis. So you can read about that in your electrical circuit theory. Okay, so how the voltage division can be done in order to reduce. But here we just look at the structures of the circuit. So your understanding will be tested based on how pi network can be different from T network. So it will be more general, not many mathematical expression needed. Okay, so virtual resistance can have any value as long as it is smaller than RS and RL. So they're asking why. So because we want to bypass. Okay, so if the other values are higher, so it cannot bypass. Okay, so it cannot bypass, and we can see it is connected in series. Okay, so it's connected in series. In between, you have a virtual resistance. So these two elements are connected in series. Okay, so it will produce a small virtual resistance. Okay, so the formulas are the same. Okay, so value of virtual resistance is usually defined by the desired circuit Q. So as I said earlier, so circuit Q is determined by the person who designed the circuit. Consists of the modulated signal, and uh, we need to have the virtual resistance in order to determine how much to adjust for the antenna to function at the optimum level. Okay, so we see some example. So design a pi matching network to match a 100 ohm source to a 1 kilo ohm source. Okay, so we know the source resistance is 100 ohm, and the load resistance is 1k, 1k kilo ohm. So the loaded Q must be 15. Okay, so Q values they already gave Q1. So first find the value of the virtual resistance since circuit Q is specified. Okay, the value of Q is given. We know RL is larger than RS. So yesterday we saw the quadrant. So if RL, why RL more than RS? Because RL is 1000, RS is 100. So 1000 is more than 100. So you can get this formula. So this formula is standard. Okay, so this is from okay. Okay, so the formula is not mentioned here, but we can use this formula also. Okay, so we just apply this formula. So to calculate the R virtual, so RL over Q square plus 1. Okay, so Q is given 15. So 15 square plus 1. So 226. So once you divide, so you can see. So we can see R virtual is much smaller. So that's why the current can flow. Because you see RS is 100, RL is 1000, R virtual is only 4.42. So which allow the current to flow. Okay, so we now solve the 2L network to mesh to this virtual resistance. So once you find out the virtual resistance, then you can start to solve the other L network. Okay, for the network connected to the load resistance. So we start from the behind. Okay, we start from the behind. So XP2, we want to find the XP2. So it's actually so RP. So RP is actually RL. Okay, over QP. So RL over Q. So Q is given. So 10,000, 1,000 divided by 15. So XP2 is 66.7. Then you find XS2. So the formulas similar like yesterday. So refer to yesterday's slide. So you can see this formula. So XS2 goes to Q R virtual. Okay, so Q we know 15. R virtual we already calculated 4.42. So XS2 is 66.3 ohm. Okay, so we already found this, all these values. So even R virtual we already found. Then we move to the front one. Okay, so we move to the front box. Okay, for the network connected to the source resistance, so Q equals to RS over R virtual minus 1. So 100 divided by 4.42 minus 1 square root. So Q, because here the Q is different. So why the Q is different? Because it's connected to the source. Okay, so connected to the source, so we get 4.6. Okay, earlier it was 15. Okay, so because this is the loaded Q. This is the source Q. Okay, source Q. So you determine based on the source resistance. Okay, so the Q is different with the specified Q. Again, the circuit Q is defined with the branch with the ISQ. Okay, so we try to take the ISQ. Okay, in order once we complete. But for individual analysis, so for here we take the loaded Q. For the front part, we take the source Q. Okay, so we can choose the IS. Okay, so for the network connected to the source resistance, so we can calculate. So this is yesterday's formula. XP1 equals to RS over Q. So Q we calculated 4.6. So RS is 100. So XP1 is 21.7. Then once you find XP1, then you can find XS1. So this is the formula yesterday also. Okay, so Q is 4.6. R virtual is 4.46. So we can get, so the value here is 20.51. Okay, so at these values, so the source or the signal can be transmitted in an optimum condition. Okay, so this is the resulting network. You can see, so RS is 100, XP1 is 21.7, XS1 is 20.5, XS2 is 66.3, XP2 is 66.7, and the load resistance is 1000. Okay, you are left to specify what type of element to use. Okay, so XP1 and XS1 are the opposite type. So it's a opposite type. So we can determine. Okay, once you already calculated this, so we can determine. So we can see here. So there are various type of setup for the pi network. So here you can have both inductance and the capacitor at the sides. So you can have this kind of a setup, or you can have this kind of setup. Okay, so 20 you can have two capacitor on top and two inductance in parallel. So we can have so one inductor and also one capacitor, and in the both legs we will have one each. and we can have the opposite of this circuit. But the impedance of all these components will be the same. So we can see all the same because it will produce the same output. Okay, for you to transmit. Okay, so that's on the pi network. So we see another type of network. We call it as a T network. So again, so the network topology appears to be a T. So you can see it's a T. So the name of the network is because of the shape, or we call it as a topology. Okay, so you will encounter this term after this topology. Topology is like architecture of the network. Okay, so similar to the pi network, so it can also be thought as of S2 two back-to-back L network. So you have one network and also another network. So you can have two networks. So that's why you can see there are at least minimum three elements inside. Okay, X1, X2, and X3. So RS is available and RL is available throughout the analysis. Okay, so we see about this. So for similar to the Pi network, it is designed to match with a larger virtual resistance between source and load impedance. So compared to Pi network, the R virtual is smaller, but for T network, the the R virtual is larger because it is connected in parallel, not in series. Earlier, the Pi network, so you can see the elements on top are connected in series. So you can have a virtual resistance of which is much lesser. But for T network, so you can see it is connected in parallel to the virtual resistance. So you must have a larger. So if you have a smaller virtual resistance, then the circuit cannot function properly. Okay, so because all will pass by here, so nothing will pass by here. So it will have some problem. Earlier you have the elements here and here to control, but if you don't have, so once it pass by here, so you see there are certain resistance here, so it will try to take this part, which will cause the component to damage, and also there can be a lot of errors. So you need to set this almost equals to this element so that it can allow but at a certain resistance. Okay, so T network, so design of the T network is the same as of Pi network. So difference is that the virtual resistor should be larger than both RS and RL. Okay, so why I already told you, so why it must be larger. So Q quality of network is approximated by, okay, so R virtual divided by R smallest minus 1. So there's a terminating resistance, okay, so which will involve in T network. So terminating resistance is some sort like a virtual resistance, but it is like fixed in the circuit. Okay, so that's another difference between T network and also Pi network. Okay, so we are not really looking into this terminating resistance, but just for your understanding, so we calculate the quality of the network using this formula. Okay, so general step for three element matching. So you find RS and RL. So we see if it's a I value, so both are above 100, then we always set to use Pi network. Usually if it's a low value, it's 100 and below, then we will opt for T network. So this is the usual practice. Okay, so proceed with L network matching starting with the branch with a larger or smaller terminating resistance for pi and also t respectively. So we have seen we start from the right. So earlier we solve here, we solve here, we solve here, then we solve here. Okay, so we'll move from the right to the left. So we can first try to solve the R virtual. Okay, then solve the reactance for the other L branch using the new Q defined by R virtual. Okay, so similar like how we saw the example for pi network. So similar. So initially you will be given the load quality, or you need to calculate the load quality. So based on that, you determine the R virtual. Then using the R virtual, you find the new Q for the source. Okay, so based on that, you can determine the values of all the missing variables. Okay, so you combine element of x1 and x2 for pi network and xp1 and xp2 for t network, and you compute the actual capacitance and inductance value for the reactance at the frequency of the operation. So these steps are for the practical transmission, okay, in the industry. Okay, in the industry, so you first you have a modulating circuit, you already prepared, you want to join it with the antenna, so you need to find the impedance matching. So once you have the impedance matching, then you can send the signal. Okay, so you send the signal at the frequency of the operation. So let's say it's 100 megahertz. So you can send. So you must have an impedance matching to calculate the actual capacitance and inductance needed to transmit at this particular frequency without any distortion. Okay, so that's the step of three element matching. Okay, so earlier we have seen for the for high quality. So there can be some application which requires a low quality matching networks. Okay, so pi and T matching network are usually used for narrow bandwidth, which is high quality application. So narrow bandwidth, I already explained before this. So the frequency range will be narrow. Okay, so usually it will be used for high quality application. So what if we need a matching network of wide bandwidth? Okay, so wide band meaning so the frequency range is very high. Okay, so usually it will be used for low quality applications. So this can be achieved by connecting L networks end to end or series stack instead of back to back. Okay, so I will show you. Okay, so you can see achieved by connecting L network end to end. Okay, end to end meaning it's not here. Okay, so end to end. The picture is not here. Sorry. Okay, so end to end means so it's connected in series. Okay, so connected in series, so one after one, cascading. So it will pass by the component one first, then it will go to the component two. So back to back meaning so it's like this. It's like this, so back to back. So we don't prefer this. Okay, so a low quality matching network, so maximum bandwidth, which is lowest quality, can be achieved when R virtual is equal to geometric mean of RL and also R. So you want to find the square root of RS times with RL. So you have RS and you have RL. So you times the value. So earlier, let's say 100 times with 1000. So you times, so you will get 100,000. So you square root 100,000. So you can get the virtual resistance. Okay, so you can get the virtual resistance. Okay, so here you can see this is one network and this is another network. Okay, so earlier we have seen how it was. So compared to, so you can see, so this is more back to back. Okay, so one, so is connected. So the R virtual is in between. But for Q network, so you can see, so it will pass by one element. So you will have one, then you have a virtual resistance, then you have another similar concept. Uh, so you call it. So this is one end to end, and this is another one end to end. Okay, so it's considered like a series. Okay, so low quality matching network. So the loaded quality of the network. So we can calculate using this formula. R virtual divided by R small minus 1, or we can use R large over R virtual. So depends on which network you want to calculate. So if you want to calculate for load, so load usually will be higher. So you take the virtual, you take the large value, divide by the virtual value minus 1, then you can calculate the value of Q. Okay, for even wider bandwidth, we can cascade more L networks end to end. So as I said, cascade meaning, so this is one. So you cascade another setup, then you cascade another setup, you cascade another setup. Okay, so that is what we call as a cascading. Okay, so cascading meaning the output of the previous process become the input of the new process, and that is what we call as a cascading. Okay, so optimum bandwidth is obtained when ratio between successive resistance are equal. So this is to find the optimum bandwidth. So you want to find ratios between the successive resistance. So you need to find uh, the resistor that is side by side. Then you can take the ratio in order to find the optimum bandwidth. Okay, so this is the formula. Okay, so we conclude the chapter number 4. So it's just more on the understanding or explanation for you to understand radio transmission. So we have seen in 4 parts. So we covered last week and also this week. So last week we have seen what is the transmitter. So we have seen the classification of the transmitters. So usually transmitters are classified based on the type of modulation. So based on the transmitted frequency range. So we select the transmitter based on that. Then we have seen AM transmitters, the power amplifier modulation techniques, then the type of AM transmitters. So we have seen low level modulation transmitter. So low level usually will be less complex than the high level. So high level usually will be more complex. Then we have seen the FM transmitters. Okay, so power amplifier modulation technique, the type of FM generator. So we have a direct method, indirect method. Okay, so there are two types. Then yesterday we have seen the impedance matching network. So we have seen L network yesterday. Okay, so today we have seen pi network and also T network together with the low quality matching network. Okay, so all these we have covered. So if you don't understand, then you try to listen back to the lecture. And if you still have questions, you always can come back to me. Okay, so any questions so far?
Sir, can I
No,
ask
Doctor.
something?
Yes, yes.
So does that mean that the virtual resistance exists in both circuits, but how do we know that they're there?
Okay, so virtual resistance is actually is like a tuner. So it's like if you see the practical application, so you will have a certain kind of resistance included, so included in the calculation, so that you can tune it properly.
Is it a physical component or is it
No,
like
it's not.
a byproduct?
It's not a physical component. It's a virtual
Oh,
component. Virtual meaning is like imaginary. So, but when we are doing the calculation, so we need to consider this virtual resistance in order to have a proper tolerance when you are designing a matching circuit for your modulating circuit and also antenna. So usually, what?
Is it like a
Yes,
if I- is it like a byproduct of the two resistors?
it's a byproduct of combining, because when you want to combine uh, a circuit with the antenna, so you cannot immediately combine. You need to have some kind like a buffer in between. Okay, so this virtual resistance is like a buffer.
Okay, sir. I understand.
So buffer. So once you have this buffer value, then you can combine it, and it can operate within the tolerance. So if not, if you don't have the virtual resistance, and you calculate based, let's say, the circuit requires 100 ohm, and the antenna is having 100 ohm. So when you join together, so the circuit will blow. Because there will be energy converted into it, and also there can be sparks generator. So that's why we need to have the small virtual resistance in between, so that it can become like a damper, and it need to be determined. Okay. So any other question? Okay. So no questions.